Welcome to the deep dive. If you're like us, you completely rely on being able to connect with anyone, anywhere, instantly.
Oh, completely. We just take it for granted.
We do. We accept it as a given. But if you stop and think for just a second, what is this enormous, sprawling, hidden thing that makes it possible for your voice to reach someone on the other side of the planet in, what, less than a second? We just press a button and the magic just happens.
And we get frustrated if it takes 2 seconds.
Exactly. So today, we took a deep dive into some fascinating source materials. We're talking engineering documents, telecom history, field notes.
Right, and all of them are centered on that one big question.
How does my voice physically get from here to there instantly? It's not just Wi-Fi or satellites. It's this brilliant fusion of physics, huge engineering, and a massive human workforce.
Yeah.
We want to go beyond the simple stuff today to really give you those high-impact nuggets of knowledge you're looking for. Okay, let's unpack this. Our mission here is to really dissect the architecture of global connection.
Yeah.
Not just the tech journey of the data, but the human systems behind it, the rules, the people, everything that makes this incredible speed possible.
And that fusion you mentioned, that's really the key, what we call instant communication. It all rests on what the sources call a vast, invisible web of connection.
Invisible, yeah.
We always talk about the cloud, but the cloud is very much on the ground.
Right.
It needs physical cables, physical routers, and just constant human oversight. The complexity isn't just in the fiber optics, it's in the coordination, making thousands of different pieces act like one single network.
And that's what makes the journey your message takes so fascinating. So let's start there. Let's start with that technical journey, right when you say hello into your phone.
Okay, so the very first step is digitization. Your voice, which is an analog sound wave, gets converted into an electrical signal, and then almost instantly, that's translated into bits, ones and zeros. But here's the crucial part. That digital stream, it doesn't travel all in one piece. It gets broken down into these small, manageable units.
We always hear this analogy that your voice turns into tiny, invisible packets of light. But let's clarify what that really means for how it's sent. Why break it up into packets? Why not just send one long stream?
That's where the genius of packet switching comes in. It's all about efficiency.
Okay.
Imagine you're sending a giant encyclopedia. If you send it as one single file, that whole line is tied up. Nobody else can use it.
Makes sense.
But if you break it into individual pages, those are the packets, each page can take the fastest route available at that exact millisecond. They might even take different physical paths.
So different parts of my one sentence could be traveling on totally different cables.
Totally different cables. And it means if one path is jammed up, your data just finds another way. That's what guarantees the speed and the reliability.
That makes perfect sense. It's like real-time traffic optimization. So these packets race out of our phone. Where do they head first?
They have to find the core network. So they're racing to the nearest cell tower or maybe a junction box in your neighborhood. Those towers, they're the on-ramp.
The on-ramp. I like that.
But what happens after the tower, that's where the real infrastructure begins. That tower is connected to the backbone through something called a backhaul network.
A backhaul.
Yeah, and sometimes that's still a high-speed microwave link, line of sight between hills. But more and more, especially in cities, that cell tower is connected by fiber optic cable directly to a regional switching station.
And that switch to fiber must make a huge difference.
A huge difference in minimizing that initial lag, what we call latency.
Okay, so our packets have found the fiber superhighway.
Yeah.
Now, this is where we get into the physics of it. We always hear data travels at the speed of light. But is that really accurate when we're talking about glass cables?
Here's where it gets really interesting, and this is a fantastic technical nuance for a learner like you. Yes, the data is traveling as pulses of light, which is incredibly fast, but the speed of light is only at its absolute maximum in a perfect vacuum. When that light travels through a fiber optic cable, which is made of ultra-pure glass, it runs into something called the refractive index.
The refractive index. So you're saying the glass itself actually slows the light down, even if it's just a little bit?
Precisely. The light is constantly, reflecting and bouncing off the walls of the glass fiber. So in reality, the data is traveling closer to 70% of the speed of light.
Wow. Only 70%.
It's still staggeringly fast, something like 125,000 miles per second. But that slight slowdown, that's one of the hard physical limits of our networks. It adds just a few milliseconds to a round trip across an ocean, but Those milliseconds really matter to the engineers.
That's a perfect non-obvious detail.
Yeah.
So these packets, they're zooming through these glass cables, which the sources say are thinner than your hair.
Yeah.
But how does that tiny signal stay strong across, say, thousands of miles under the Atlantic? It must degrade, right?
Right. It absolutely degrades. That's a constant challenge. Light pulses naturally spread out and get weaker over distance. So the solution involves these really sophisticated components that are embedded right into the cable itself. They're called repeaters or amplifiers.
So they're boosting the signal along the way.
They are. For these huge submarine cables, they build these optical repeaters every 40 to 60 miles along the entire path. And they don't just boost the signal, they actually reshape and clarify the light pulse so it doesn't just turn into noise.
And these things are at the bottom of the ocean.
Bottom of the ocean. They have to be incredibly tough, powered remotely from land, and built to last for decades without anyone touching them. It's just colossal engineering.
So the journey is a series of light-speed sprints with these little stops for signal rejuvenation.
That's a great way to put it.
Okay, so the packets finally arrive near their destination city. How do they know which provider's network to jump on or which specific line is the fastest at that moment?
This is where we move from just physics to, well, business and logic. It's the real genius of the modern internet.
Okay.
The packets hit a regional backbone and they head for these massive buildings, what we generally call data centers. But to find the fastest path, they need to go through something called an Internet Exchange Point, or an IXP.
I've heard that term, IXP. Are they just really big, fancy routers?
They're much more than that. An IXP is a physical place, usually inside a huge data center, where all these different independent networks agree to connect their gear directly to each other.
All in one room, basically.
Pretty much. And this is crucial because it's where they set up what are called peering agreements.
Peering agreements.
Think of it this way. If my network wants to send data to your network, I could send it the long way around through a third party, which costs money. Or we connect directly at the IXP and agree to exchange our traffic for free, or at least very cheaply. So these IXPs and these complex peering agreements, they are the invisible hand that's guiding your packet along the fastest path. The router isn't just looking for the shortest wire. It's looking for the most efficient, least congested, and often most direct peering relationship it can find.
That completely changes how I think about routing. It's not just a technical choice. It's a socioeconomic agreement that's happening over fiber.
Exactly.
So this entire process, the packetization, the backhaul, the speed of light minus refraction journey, the reamping, the IXP routing, it all happens in less than a blink of an eye.
Mm-hmm.
What part of that delay is the actual travel time versus the time spent, processing in all these routers and switches?
That's the definition of latency. And the research shows that even on the absolute best routes, the physical travel time is the biggest factor. It's usually about 80 to 90% of the total delay.
So it's mostly just distance.
It is. The routers at the IXPs are unbelievably fast now. But you can't beat the physics of distance. When you call someone 5,000 miles away, you're dealing with a round trip of 10,000 miles, and no amount of computing power can change that fact.
Truly insightful. So we've established the tech is a marvel. But as we said at the start, this deep dive is only half done if we don't talk about the human infrastructure, the people who design, build, and maintain this whole system.
Absolutely. The technology is worthless without constant, highly specialized human effort. If we connect this to the bigger picture, all those light packets and peering agreements, they all fail the moment one key piece of equipment goes down.
Right.
The system is fragile. It needs human vigilance 24/7. It is not just one thing. It's this interplay between human planning and the tech itself.
Okay, so let's break down those 4 essential human jobs from the source material, starting with the people who decide where all this stuff should even go.
These are the architects. And their role is incredibly strategic. They don't just sketch out where to put a cell tower. They're doing massive geopolitical and engineering risk analysis. If they're planning a new submarine cable, they're looking at tectonic plates, shipping lanes, fishing zones, the political stability between the two countries it connects.
The stakes must be huge.
Incredibly high. They're making decisions that cost hundreds of millions of dollars and lock in these global data routes for decades.
So once the architects draw up the plans, you need the builders to make it real. What kind of skills do they need?
The builders are the ones translating that digital plan into physical reality. I mean, this is everything from laying deep-sea cables with specialized ships and ROVs to, trenching fiber through solid rock. But on the ground, a really crucial skill is something called fusion splicing.
Fusion splicing. Tell me about that.
Yeah. So remember, the data has to travel through a continuous piece of glass. Fusion splicing is this highly technical process of aligning the cores of two fiber cables, we're talking microscopic, and then using an electric arc to literally weld them together. It creates a connection so seamless the light signal barely even notices it passed a join. Without expert splicers, the architect's perfect plan just becomes a bunch of weak, useless links.
Incredible. So the infrastructure is built, the light is zipping along. Now we have to protect it. Who keeps all those billions of conversations safe as they fly through all these different networks?
Those are the digital guardians, and their job is way beyond just simple IT security. This is network security on a colossal scale.
Right.
They're the ones designing the encryption protocols that wrap around the light packets, and they are constantly on the lookout for threats.
Like what kind of threats?
For example, they're the ones who have to detect and stop a DDoS attack, a distributed denial of service attack.
Ah, I've heard of those.
That's where someone tries to flood the system with junk data to clog it up. A digital guardian has to be able to spot that weird traffic pattern instantly and divert it or filter it out, all while keeping all the legitimate traffic flowing.
And finally, you have the unsung heroes. The people who have to fix things when they physically break. A storm, a ship's anchor, a backhoe.
Those are the technicians, the critical maintenance workers. They are all about continuity. They're the people who still have to climb towers and fix cables to make sure no one ever loses their connection. And their expertise is just huge. From running advanced diagnostics to doing physical repairs in really dangerous environments. When a major submarine cable gets cut, it's a technician on a repair ship guiding a robot to pull it up from the ocean floor, bring it on board, and do that high-precision fusion splicing right there on a rocking boat.
That's amazing.
Without them, that whole high-speed race comes to a very sudden, very expensive stop.
It's really humbling to think about. That instant connection we expect every morning depends on all this specialized physical and intellectual effort happening all over the globe.
It really is.
We've gone from the physics of light and glass to the business of peering, all the way down to a technician splicing a cable in the field. The source material had a great unifying idea for this. It said telecommunications is like a bridge made of people and technology.
That bridge metaphor is perfect. It really captures the interdependence, the technology, the fiber, the routers. That's the structure of the bridge. But the people, they're the active intelligence. They're the ones who planned the route, laid the foundation, and now they're constantly managing the traffic to make sure that bridge stays open.
Yeah.
And if you look at the deeper purpose of it all, this incredibly complex machine, it's really serving a profound human need. The world isn't just connected by wires and signals. It's connected by our shared hope to reach out, to share stories, and, to bring everyone closer, no matter how far apart they are. The instant speed is just the efficient way we fulfill that very human desire.
That's a powerful way to look at it. It really reframes what connectivity even means.
Yeah.
So what does this all mean?
It means that the next time you connect instantly with someone, you can understand that it all depends equally on these invisible packets of light moving at immense speed, and on the dedicated labor of an architect who planned for geopolitics, a builder who did a perfect fusion splice, a guardian who maybe just stopped a DDoS attack, and a technician who just fixed a severed line.
It is a collaborative magic act, really, just to get your message across a continent.
It is. So for your final thought, next time you connect with someone instantly, think about this. Don't just consider the fiber and the speed. Consider which specific, highly technical human role made that connection possible in that exact moment. Was it the architect's foresight years ago? The builder's perfect weld? The guardian's split-second security decision? Or the technician's dangerous repair? They are the essential, unseen intelligence behind the light.